And we're live. Take it away, Tamer.
Hello, everyone. Welcome to the monthly audio programmer meetup. My name is Timur. I'm your host tonight, together with Josh. Hello, Josh.
Hey.
Yeah, thank you so much for tuning in again. Welcome. Today is actually 1 year since we've started doing these online, right? So our first online meetup was exactly 1 year ago in April 2020. So it's been a hell of a year. Well, thank you so much for staying with us. And to those of you who are new here, thank you so much for joining us tonight. I need to apologize in advance. I'm experiencing technical difficulties tonight. I have this LG Ultra.
And he just, right when he said that, he broke out. Yeah, so Tamer's been having a little bit of technical difficulties with his audio and video tonight. So I will segue.
Hello.
Oh, there you are.
Yeah. So I was just about to say, I have this annoying technical problem that every few minutes, like everything just disconnects, and I just couldn't like fix that right now. So there's nothing really I can do about that. I really apologize. I hope it's not going to happen too often and it's not going to be too annoying. Oh well. So we have quite a few wonderful guests tonight with us. But before we get to that, Josh, I guess you had a few announcements, right?
Yes. So first of all, we would like to thank our sponsors, Sonics, Focusrite, and Juice, for sponsoring the Audio Programmer Meetup, and they've been very supportive of us. And we always want to thank you for your support. And also just wanted to talk about our audio programming community on Discord. So I'm just going to share my screen really quick so you can see. And we have the audio programming Discord that is live, and we have over 5,500 members now. And you can come join us on the audioprogrammer.com/community. It's a great place to meet other audio developers and to talk shop about DSP, about build systems, about IDEs, about C++ and JavaScript and everything else related to audio programming. So there's the place where you can join us at theaudioprogrammer.com/community. And also wanted to talk about a few roles. So we have some clients that we work with on the recruiting side for contracting and permanent roles. And we have quite a few roles that are out there at the moment. So if you're an experienced Juice or audio developer, come check out the roles that we have. There are quite a few of them, and you can find those on theaudioprogrammer.com/roles. And from there, I think we can just go ahead and segue into our first talk, and I'll let you introduce that, Tamer.
Right. So before I do that, just a couple more things. First of all, if you want to speak here at our monthly audio programmer meetup, which takes place every third Tuesday of the month.
Second Tuesday.
Yes, every second Tuesday. I'm so sorry. Today I'm confused about the times. Yeah. So yeah, every second Tuesday of the month. If you want to participate in that, if you want to give a talk here, you're very welcome. Please submit your idea or your suggestion at theaudioprogrammer.com/submit. And then the other thing is that if you're watching the YouTube stream and you have questions to any of our speakers during the presentation, please feel free to ask them in the YouTube chat. And if you want to help us, please prefix the questions with the word question in capital letters, because then it kind of stands out in the chat and it's going to be easy for us to see it and then ask it, after the talk or even during the talk, depending on how it goes. So with that, I'm very pleased to introduce the first talk. So tonight we have the team from GPU Audio here with us. Welcome and thank you so much for joining. There are quite a few of you, so I'm not going to introduce you all by name. Instead, I'm just going to maybe let you introduce yourself.
Yeah, so please meet me. I'm Sasha. I'm co-founder of GPU Audio, one of the architects of the original technology and platform, the entire solution, and one of the, concept creators. Today, please meet my co-founders, CTO Alexander.
Hey, everyone. Very nice to be here. Thank you for the opportunity. I am the Alexander Prokopchuk, the CTO of the GPU Audio. Please forgive me that my current image and sound are not ideal. I'm currently on the road, so I don't have my favorite SM7B with me, so sorry for that.
Yeah, Alexander helped us a lot to write down the DSP, redesign them, and fit to the systems like a GPU. And please meet my co-founder. He's right here with me, Basil.
I'm Basil.
Yeah, he's our chief product, and this is the first guy who came to me with the idea creating the GPU audio technology. I was thinking previously that it would be quite easy. Well, you know, a few plugins on GPUs, not a big deal. But then it turned into the entire new standard we will talk today.
Fantastic. Right. Yeah. So what are you going to be speaking about today?
So today we will show you the web demonstration about how the technology, what is the technology is about. We'll show you the hardware setup we have today, and this hardware setup and some software we developed so far. This will stream directly to the Zoom conversation, and I believe it will be streamed directly to the YouTube, so everyone can hear that it works. Everyone can see that it works at low latencies. It works remotely between the two connected together laptops, which is another scenario. And we want to prove to everyone that it's actually possible to maintain GPU processing at latencies as lower as 1 millisecond, including through the local network, whatever it is. So we want to show this use case. We also want to talk a little bit about the technology, how it was possible, how it was done by us, what are the key challenges we accomplished so far, what we are going to do with this technology, with this platform, what we want to, you know, what the message we want to deliver to the Prodia community. And if you allow me, I'll start.
All right. So yeah, I guess you're ready for you to start. I'm really excited about this because, you know, the topic of audio on the GPU is really quite new and exciting. And when we saw your proposal, we just knew we had to get you on the meetup. And so, yeah, take it away.
Before we start, really quick, for people that are in the chat that may have questions, please prefix any of your questions just with the word all in caps question, just so we can see that and we can ask the GPU audio team after their presentation.
Okay, let's crack on. So first of all, guys, let me show you what we have for today, what we will stream today. This is a MacBook I used to, this is another Zoom window. This is just a MacBook I used to speak with you. And currently with my phone, I'll show you two particular laptops. This is a Gigabyte Aero that has the RTX 2080. We currently don't use the RTX 2080. This is the client side, as you can see.
Sorry, I don't think you have the camera switched to the device because I don't think we can see it.
In another window in Zoom, actually.
Oh, is that being streamed into the?
Yeah. I just put it back to gallery view so they can see it.
Okay, cool. Thank you, Josh.
Yeah.
Sorry for that.
All right. So may I ask Basil to stream, you know, the client side window, which is the Reaper.
Oh, sorry. Let me.
Can you see this?
Turn on the
just one second. Hold on. All right, guys. You have to see the Reaper window, right?
Yep.
Yeah, great. So here you can see the ASIO. What is this? Guitar Rig Mobile with 96 kilohertz, 96 samples, 1 millisecond buffer latency. This is the client side. So what we will do with this Gigabyte laptop, we will offload the entire tracks. We will process here through the Thunderbolt-free connection. If you can see this, I'm sorry. This Thunderbolt-free connection to this one laptop, which is their Razer Blade with another RTX 2080 with the server running on that GPU, I'm sorry. So maybe we can start with one simple delay, and you will see this. You will see this working, and you can hear the result. So, shall we start? All right. Let's open the effect. So guys, I hear that you hear that there is a sound, right? 1 millisecond latency. So I'll ask Basil to add more processings, like one simple delay, and you can hear the result. And, oh, sorry. And here is just the simplest delay. Not sure if I can show you the traffic. Could you open the task manager? The traffic goes through the Thunderbolt 3. As you can see on my phone, sorry, the GPU 0 is Intel UHD, and the discrete one, RTX 2080, is not used, but the traffic goes through the Thunderbolt 3 connection with one simple delay, 8 megabit per second utilized. And here as well on the GPU server, the traffic started, and the RTX 2080 actually started work. If I'll ask Basil to duplicate this track, just simply duplicate this, you can see again on my task manager, please show it, the traffic went, doubled with double size, as well as here on the server side. And also the GPU one also doubled, but this is not actually the payload. It's just the driver calls, and that's why Windows show this in double time. So what I will show you right now that we actually managed to work it within 1 millisecond latency. Maybe Basil, you have to turn knobs, and let's speak about the simplest delay. Let me switch everything on. Yeah. So what you see right now and hear right now is just the simple delay with infinite impulse response filter, with the tape effect and feedback loop and these sort of things. I'm sure that you can hear them pretty well on the YouTube. Do you guys? I'm looking on the YouTube chat. Do you guys hear it? Do you guys hear any difference? Oh, okay, I hear it. Okay. So, okay. What I will ask Basil to do, just to duplicate, like more delays. And then I'll ask Basil to follow contract and let me hear some changes. So you can see that we also utilize the initialization step. It requires some time, to run the GUI and etc. But anyways, I'll ask like add the up to contract, like there and lower. Okay, we have like technical issues. We have to restart just for a while. Sorry. What I want to say is that this works through the network connection, and we use the RTX 2080 on the Razor blade, and this is delivered across the 1 millisecond latency, the round trip, right? So what we have on the client side, this is the ICO for all drivers utilized, and we can run any sort of the processing remotely or locally. It doesn't matter at all. So I'll ask Basil to restart it and just to make more tracks, and you can see that actually traffic goes. And then I will ask him to add like different effects developed so far. So for today we developed delay, flanger, chorus, phaser, multiband distortion, parametric equalizer, exciter, reverb. We're rolling out the reverb, the hybrid one, and we also implemented some compressors with emulations. We have some technical issues because it's an alpha version. There are some bugs anyways. So let's start over. Let's start over to add more things. Could you show like something else, like not delay? I don't know, like anything else.
Sorry, Sasha. I see in the chat that the viewers are saying that we should do the DAW signal louder.
So Basil, please just add, very few effects and then just. Okay, he needs to turn on the demonstration again. Yeah, so we have many more of them. I'm not sure whether we can show all of them right here, right now. This is like the alpha version. The alpha version we are continuously rebuilding and testing. So that's the reason we don't have it in public yet. But I believe that will be containers.
Одной веры на двоих, жизнь, лифт, вверх-вниз. Черновик картины, снова чистый лист. Она опять будет сидеть блок до утра. Поиск правды, под стук дождя, крутить слова в голове, чтобы понять, что произошло тогда. Он же сказал, вернусь, дождись меня. А дальше стрелки, часы, он навстречу, как-то хмуро. Конец разговора, пуля, дура. И, наверное, он знал, что все не так просто. И это кино для взрослых, где он уже не вернется. Но он улыбался тогда так спокойно. Жаль, что жизнь одна, но она того стоила.
Right, anyways, because we have an effect with more devices, more planters whatsoever, it will work. With 1 millisecond later, and maybe we can add more, different effects with different types of effects, and use the solo modes, like here, like phaser, I don't know, like anything like that. Yeah. So this is use the exciter, I don't know, and show like exciter notes and that stuff. Are you guys? Yeah, I hear it. Great. For more cool stuff, we can show you more cool stuff, and also we want you to go to the gpu.audio website to register for the beta. If you can do that, please do, the community, because we need to help us to build these stuff, to sign up for the program that will start pretty soon. So basically, you can show photos once again, and you can add more tracks, like delayed tracks and that stuff. And then I will show again the traffic, and then I will break the connection. You can see that do this in real time. Yeah, Josh.
Одна жизнь, одна свобода, как один бой длиной в многие годы. Он отрабатывал удары столько долгих зим. Теперь он понял, нужно.
We can't hear what you're saying over the music because the music's too loud. It's actually in our ears now. But
sorry, it's real time.
Yeah, I think there are a lot of people are really impressed with what you're doing here. I think there are a lot of questions in terms of the how you're doing it. So it's great to hear what's happening under the hood, what sort of API you're using, and just digging a little bit more into the technical details.
Okay, can I just do the last thing, in this demonstration so everyone will believe it? Because for me, it's very important because people started arguing in the web forums that it's impossible to do. The GPUs are very, high latencies and that stuff. So I want you to show, sorry, 1 second. Okay, guys. So I wanted to show you, this is traffic here on, this is traffic here on the GPU server and GPU 1 in Ethernet, Thunderbolt. Oh, sorry, it's flashable. What I will do here, all right, it's crashed, but anyways, okay, you can see that it worked actually. Anyways, and GPU 1 and Ethernet, we have bags, I'm sorry, but anyways, this is something I wanted to show you that actually if we will break the connection, there will be no Ethernet, no GPU 1, but it's crashed and so on. And so these things are working here. Okay, if I can continue right here on my MacBook. Well, there are lots of things you have to do if you want to consider to utilize your GPU to process audio. Well, whatsoever you have, like desktop, laptop, GPU server, blades, it doesn't matter. If you want to process audio through any sort of APIs like BST or audio unit, you first have to understand how you can achieve the low latency work on the GPU, because this is something that you cannot do with any SDK available to this date, like, I don't know, like CUDA, like DirectX, any sort of shaders, anything. We used anything, like almost all of them to organize this stuff. So it's impossible. There are simply no such calls to organize many tracks, stereo tracks with the many channels. And there's no way you can organize all of these tracks and upload it to the GPU using some asynchronous API. There's no way to organize it. So you have to implement this. The second big problem why you cannot utilize GPUs as simple as it is to accelerate your algorithms whatsoever they are, with the recursive algorithms or well-parallelized algorithm, doesn't matter. The second thing you have to consider is that the GPU is, which is well known, is a SIM device, which means that it's single instruction, multiple data. So you can run like a very few tasks for many data. And the audio, it's one-dimensional arrays usually, right? For 96 kilohertz, 96 samples we showed you previously. For 1 millisecond, it's just 96 samples. So you have to dispatch many tracks in parallel with the tiny amounts of data if you want to organize the recording sessions, live performances, and that sort of stuff. So GPUs, from the very basic, are not designed to do the audio processing work. So how did we get this? So first of all, we implemented the component, the basic technology we call scheduler. The scheduler usually packs all of the data to the GPU. It unites all of the data in a few streams, or as many as we have the real stream, the PCI Express streams. We pack them all and we deliver from the client to the GPU server. So there are two basic things here actually. The client side, which is just the VST-based plugin we developed so far, and the server side, which runs all of the payloads on the GPU. So again, the VST plugin and the GPU server. So what we did, we implemented the copy manager for the scheduler that allows us to unite all of the data and to transfer them to the GPU server and device and return it back within latency scopes as low as 1 millisecond latency. So this is something you cannot do with CUDA, or I don't know, like OpenCL, OpenGL, DirectX, Vulkan, whatsoever, Metal, I don't know. This is something you cannot do, but you can do this using the driver API and the low-level API, which is for the NVIDIA cards, PTX ISA. This is like a cross-platform assembler NVIDIA developed for all of the NVIDIA GPUs so far. So this is how we managed to run many streams. And you can find some videos on YouTube that are related to these cases, remote computing cases that we run 45, 90 channels and even more within 1 millisecond latency. Actually, in tests, we do run hundreds or even thousands of streams without the VST API, because the VST, it limits our bandwidth because we cannot manage threads of the DAW. So this is a minor issue, but whatsoever. The second thing you have to consider in order to implement GPU acceleration of the algorithms is how to make GPU running many different tasks. Because, for example, for the infinite impulse response filter, there are feedback, right? This is just the nature of infinite impulse response filter. In classic design, you cannot parallelize infinite impulse response filter, but there are some parallel designs of it. And for example, for reverbs, or for the convolutions utilized in the convolution reverbs, there are thousands and thousands, or even hundreds of thousands of multiplications. So you have to figure out how you can run 1-2 threads algorithms on the GPU, as well as how to run, I don't know, like hundreds of threads in order to deliver results in time. So for this purpose, we implemented in the scheduler algorithms that turns GPU from SIMD device act as a pseudonym device. So you can dispatch many requests coming to the GPU in real time in low latencies with whatsoever processors are, like I don't know, like delay with the infinite impulse response filter, like 2 threads utilized, 4 threads utilized, whatsoever. For the reverbs, 256 threads utilized, it doesn't matter. So you have to understand how you can run it. We also achieved this with utilizing PTX ISA. So the core technology was implemented on the top of the cross-platform PTX ISA, and soon we will develop the same stuff for the AMD Radeon GPUs. So this is how to actually organize the payload from the GPU server to the exact device. But the platform itself, the technology we used, it's very complex. It has many more components I want to talk a little bit today. So as you saw today, there is a Reaper DAW, and we run the VST plugin, and we have like a fixed chain on the very bottom, 10 cells length chain, and you can instantiate any sort of effects you developed so far, whatsoever it is, delay, I don't know, like multiband distortion or phaser and that sort of stuff within this fixed chain. So basically, on the VST part, we implemented our own VST plugin that represents the 10th length fixed chain. And for this purpose, we used many advanced features, advanced technologies that are not in the common use in the Juice community or the BST community so far. For example, we utilized Ceph, Chromium Embedded Framework, and JavaScript to render any GUI we have so far. I will show you on the very end of my speech how we did that. This allowed us to recreate any sort of GUI with photorealistic quality, 4K, high definition stuff whatsoever, just as making the website, you know. And we embedded the Ceph as a Chrome-based browser directly into the editor of the VST part. I saw that there were quite some attempts to bring in the Chrome to the Juice and to the VST. So far as I know, is that the only companies utilized the Ceph in the production area is just BioSFX, which is the positive Greek company. Or I can mix some names whatsoever. They only managed to do so. We used this Ceph in order to reorganize the GUI rendering part, because this is the first engineering task you have to solve. So for example, for the Gigabyte or for the Razer Blade we have today, we have basically two GPUs. One is Intel UHD, which is typically embedded into the Intel-based desktop, laptop processors, right? And well, the AMD APU, they have also sort of the embedded GPU solution, and the discrete one. For the discrete one, for the laptops, it's usually the NVIDIA GPU cards. If you have a modern laptop, like 3 years old, maximum 5 years old, it's 100% that you have the NVIDIA. For Mac OS X, for sure, right now it's complicated because, well, they switched from the NVIDIA GPU 5 years ago to the AMD Radeon, and right now they rolled out their own silicon, so it's quite complex for them. And we used Ceph in order to tell that to tell to editor, okay, you don't need to render these knobs and buttons by NVIDIA discrete GPU. You have to do it with the Intel UHD. So that's how we solve this problem, offloading all of the stuff on the discrete powerful GPU. So we utilize Ceph to render the GUI. Another thing, we have this like advanced technology, I called it. So the protobuf.js. This is actually the binary serialization stuff. And the binaries, Basil wanted to show you that it works actually in web. Yeah, you can show this F12, you can show them, they will see that anyway. So as you can see, guys, this is a web-based. You can run it right here locally or remotely, and I will return back to this topic because we developed more than that. So as you can see, everything is web-based, JS-based. You can do any GUI like by click of the fingers, which makes lots of sense. So more cool stuff we used is protobuf.js. Why the binary serialization is very important for the product developers community. Because guys, if you have like really hard and complex things to deliver to the end customers, like, I don't know, like modular synthesizers, tens and tens or even hundreds of variables you're utilizing in your code. So without if-else's switch cases, you can use the binary serialization, and Cap and Proto and protobuf.js is definitely the shortest way to organize any sort of data flow between any component you're utilizing. Like on the JS side, we have protobuf.js library we complemented with the community. So we linked all of the knobs, all of the data using the simplest protobuf without any if-else's switch cases. And every time we want to deliver the knob changes to the processor, minimizing the traffic, right? We send on we use the protobuf library, and we also support the protobuf library across the editor, VST editor, VST processor component, as well as GPU server component, and some sort of the integration for the device side. So again, we utilize protobuf in order to deliver the change sets on every, I don't know, like millisecond, microsecond, whatsoever they are, right into the time across all of the call stack directly to the device. And we also utilize protobuf in order to return back the data, audio data, spectrum, and that sort of things. So protobuf is another key component of the whole platform and the entire core technology. We also utilize the IPC components, inter-process communication. I know that lots of lots of things I'm describing right now, maybe it's very, very complex for you, but I want just to show you why we use it. So we use the inter-process communication like Windows-based, because we have this implemented currently for Windows and NVIDIA first, and we can do data exchange in between the plugin, BST plugin, and the device within latencies as low as even lower than 1 millisecond with IPC. So you can run this across any hardware setup use case you have it. So imagine you have like a studio with GPU server, right? Like let it be Windows running 3 GPUs, and you have like tiny rooms with the client side, with I don't know, like laptops without discrete NVIDIA GPU whatsoever. You can connect using the Ethernet cable, Thunderbolt, Wi-Fi 6E, whatsoever. You need just 1 gigabit per second. And utilizing these IPC components, you can deliver the data within 1 millisecond latency. How about that? So that's actually what we streamed today. We didn't want to show you the local setup, well, because it's okay, we managed to run latencies locally, right, on the single device, like laptop or desktop. We wanted to show you that we also implemented the IPC components, so we can deliver the data through the network in latencies as lower as 1 millisecond. So this solution, if you want to develop the GPU audio SDK-based solution, you can run it both for recording, both for live performances and concerts, and post-production whatsoever, because it supports, the solution supports the IPC components. So the typical stack again is VST plugin part, which is the editor-based is Ceph running the JS application. Then it goes through the controller integration to the processor part of VST. It unites all of the data for the all effects if you turn the knobs or if you perform in the automation lines for that. Then using the IPC across all of the way, you're packing the data using the protobuf, sending it to the another component GPU server, which could be run on local PC, laptop, desktop, whatsoever, or remote one. Then you're dispatching this stuff using the scheduler, making cool stuff computed, and return it back. So this is like very brief understanding of what we're doing. Maybe you want to ask questions here, any of you?
Yeah, so there are quite a lot of questions. There are quite a lot of questions on the chat. I can maybe just ask some of them, because I think even if some of them you answered in the chat, I think it's still beneficial for people who are watching the video afterwards. So there were quite a lot of questions on like what API you're using. I think you kind of answered that now. So, but like there was there's one question by Pavel Kopot saying, does this mean that you actually wrote a custom driver for this specific RTX 2080 on a GPU server? Is the GPU server still capable of using this GPU for driving its display?
Yeah, this is a good question. The answer is no. We're utilizing the driver API, and we're utilizing sort of, we call it, let me call it injection, our own custom-made code on the top of the driver API and PTX ISA in order to inject the scheduler, like sort of middleware, firmware for the GPU, but we do not utilize any interruptions and that stuff. We're actually not fully controlling the GPU, but we do that with some tricks applied to that. So if you do some system setup, as we did for this web demo for today, you would be able to isolate your discrete GPU and make it computing, only the audio processing thing. So no, we are not implementing any driver, but we do some top on the top of that. So that's how we are bringing the entire technology, and that's how we lowered latencies as low as 1 millisecond or even lower. And that's how we are able to run everything as you saw today.
But it sounds like you need 2 GPUs, right? You need one for like the usual screen and everything, and another GPU for all the stuff that you're talking about, right?
Yeah, but the good point is that, well, this is, first of all, if you want to be sure that you can do the work with latencies as low as 1 millisecond, yes, you have to get 2 GPUs. But the good point is that 95% of laptops, accordingly to the Steam statistics, they have the discrete GPU and the embedded GPU. Desktops, I don't see any problems to purchase 1030 passively cooled for $30, and it will do all of the stuff. For the GPU servers also, you can do anything you want. So this is not a big deal. And also maybe you guys on YouTube stream, and Josh and Timur and Paul maybe also have an interest. We started implementing this thing with the Windows and NVIDIA. This is not the limitation. This is just the point where we started. So yes, we have plans to deliver first the AMD Radeon GPUs until the end of this year to the Windows. Then we will understand what are the plans of the Apple on their silicon and their GPUs, etc. Maybe they will keep the AMD Radeon in the professional editions, so, of MacBook Pros, 16 inches and iMacs and that stuff. If they can keep it, we'll also deliver the audio unit integration for other DOS for the Mac OS X system as well. So yeah, and actually this is the reason why we implemented IPC components, because we also wanted to deliver these sort of solutions for any sort of setup that user have.
Okay, well, yeah.
Can I continue?
Yeah, sure. I thought you made a pause, so I can ask another question, but just keep going, and I'll ask more questions when you're done.
Yeah. Well, the reason why there were some attempts here actually in utilizing the GPUs for pro audio acceleration, like Liquid Sonics. Let me name of them: Liquid Sonics, Acoustic Audio, Neil Schneider. They released some products, but the problem was first latencies, and they cannot manage to run in latencies as low as 1 millisecond. They only managed to run it with 2,000 samples more, or even more than that. And they cannot manage to run many instances with different types of software simultaneously, which makes a lot of sense. So we have to bring sort of SDK and API. And right now I'm continuing my speech to what we want to bring to the community and why actually. So we developed this proprietary technology scheduler. It will be not open, unfortunately. First of all, because it's quite complex. I believe that not every NVIDIA guy understands what we did so far. Me as HPC scientist and other guys, we have like six PhD or even 7 PhD people working in the GPU audio. And it's quite unique technology how we managed to run lots of streams, like virtual streams, tracks, and channels, and dispatch them within 1 millisecond latency. So there's no point to open the technology for the rest of the users because they don't know how to improve it, right? So, but the good point is that we want to make it for free for everyone to contribute to the GPU audio-based products in the future. So we are announcing that we want to publish the SDK soon. I'm not gonna disclose the exact terms because this is again the subject of our understanding, because the technology is quite complex, believe me, and we do not want to share all of the pains and the problems we managed so far. We want to share, some complete solution so you can use it with some guidelines, and it will be enough to make some good products. So in this SDK, in the future that we will publish, you will be able to write any sort of Chrome powered solution, GUI solution. It can be whatsoever you can run. I don't know, like JS based or PHP based, whatsoever GUI. It will be very easy with our own custom made stylized knobs. You can stylize any GUI like within click of the fingers. By click of the fingers, it will be very easy for you. Using the protobufs, you can Google it. It's very easy to organize, controller part, bring in the controls to the processors. Just writing down the proto file. It's very easy. You will receive all of your GUI, all of your controls on your device code very easily with our protocol generation feature in the SDK. What you will need to use in the SDK is our own implemented simplest libraries like, I don't know, like FFT, any DSP parts. I will ask Alexander to continue just within 1 minute. And you don't need to manage threads. And this is the main feature we want to implement for SDK, because the reason why people are not utilize the GPU so far, because different DSP algorithms has different problems. Let me name a few. For example, infinite impulse response filter. You cannot parallelize the classic design, but there are other designs. For example, you can make the decomposition of filter orders, and you can run them in parallel. So that's how you achieve the the parallelization process for this purpose. There are also some other designs like Mister's evaluation, zero delay filter design, and that sort of stuff that you can use as workarounds for recursive sort of algorithms. Or let me name like compressor. In the compressor, there is the detector part, and detection actually needs to check every single sample that did you break the level, did you trigger the level in order to apply the attack or release mode or not. So in this case, you can hack it. You don't need to check it every single sample because you cannot hear this. You can do that, for example, each 32 samples, like 32 threads are parallelized. So people are simply not able to hear any difference between the triggering, each one sample or each 32 samples. For sure, there are some problems with automation here, but you can use these hacks in order to deliver very parallelized code. So again, in the SDK, for the device side, we don't want you to manage threads. We don't want you to think about how to port the exact algorithm to the device. You just need to run our own library calls, like I don't know, like use the FFT, then multiply stuff, and then do something else, and this will be as easy as you can do for CPU work. So I want to ask Alexander, our CTO and DSP engineer, to tell to the community what we implemented so far, what components we implemented for the GPU, and what will be available on SDK once it will be published.
Okay, yeah. Thank you, Alexander. So regarding the DSP components that are already developed as part of the GPU audio SDK, basically the idea of the SDK is that we do not want to limit our users to the components that we developed ourselves, but to use them as an examples or use them as basic building blocks. So as Alexander mentioned, and as you've seen on the live demonstration, we have developed quite a few of classic, so to say, processors like delay, phaser, flanger, reverb, equalizer, and so on. So the building blocks of those products, they are pretty obvious. So it's IIR filters, it's FIR filters, it's frequency and time domain convolution, it's fractional delay lines, it's FFT, IFFT, it's synthetic reverb schemes, comp filters, all pass filters with delays, all kind of crossovers, band limited oscillators, distortion emulation, envelope builders, the parts that consist of digital compressor and so on and so on. Some of those algorithms, they're translating to the GPU just fine algorithmically. The good example would be the convolution. It just scales very well in both frequency and time domain cases. Is just great. With IRR filters, it's the complete different story, so to say, because each single output of the second order IR filter depends on the previous two outputs. So it's a recursion, and it cannot be parallelized directly, but we managed to develop some kind of novel approaches of cracking those things and evaluating IR filters on a SIMP device fast enough and efficient enough, so to say.
Yeah, if I can continue, Alexander, I can tell you more, guys, is that we're not just, with the scheduler, we're not just managing to run a single instance again, a single instance of the processor, let me say it. So, because processor, it consists lots of different things like, I don't know, like components, DSP components, and we actually internally by scheduler, we are managing running each of the components as part of the processor, and we managing to run many instances of these sort of processors. So it's quite unique and quite complex thing, and that's the reason I saw some questions here on the YouTube already. That's the reason we cannot just utilize already developed some libraries that developed already. I don't know, like QBLAS, QCNO, OpenCL based libraries, whatsoever. The reason we cannot utilize it because we have to tell to the GPU and the scheduler that, okay, you're running this with this many threads and blocks, and you're running this with this many threads and blocks. So we have to re-implement all of them. But the good point is that we're gonna make it. So there are pretty standard things like linear algebra methods, I don't know, like DSP methods. FFT is FFT. So far as it supports the IE 764 standard, and it doesn't produce any sort of errors, additional errors. It can be utilized for your product if you want to utilize the GPU audio based SDK. What else I can say that as a standard, we wanted to deliver more than just the code and just the products whatsoever, our own made products or products developed in collaboration with other brands. We already contacted with some of them, major one, or with minor brands or one guy army brands whatsoever, or just indie brands, just developers whatsoever. We want to bring the entire new experience for the end customers. Because imagine what we have for today. We have three types of solutions today, hardware-based, I mean. Basically, we have the Pro Tools, its own implementation, hardware implementation, universal audio hardware implementation, and again, well, some other stuff, CPU-based stuff, even the Wave sound grid stuff. So what happens there? Well, Pro Tools, they're developing once per decade the entire hardware set, right? And they need they cost like $1,000 or even cheaper whatsoever. They are not. They doesn't have like how many, like thousands of cores. They have like 8 cores. So I'm not sure, running at 380. 18 cores running at 300 megahertz, 400 megahertz. NVIDIA GPUs, they have like thousands of cores running in 1 or even 1.5 gigahertz. And prior to the COVID times, it cost like $400-500, right? But again, even with COVID times and mining stuff, you can purchase a laptop with RTX 3060 for $900 on Amazon. Just check it right now. It's available there, or I don't know, like $1,000 whatsoever, and it will beat it. So again, this is another thing we want to bring to the industry. We want allow the user to do not just scale the power, because if you're a Pro Tools user, you can only scale it. You cannot upgrade this because you can do that once per decade. Sorry, you can just add more hardware, and here you can sell your old, I don't know, GTX 1060, purchase the new RTX 3070. You can upgrade it. Scalable, it's scalable. So, well, I know that some solutions that work with Ethernet connections, like SoundGrid, that is tuned for the performing live concerts. Imagine that you don't need it anymore. You don't need these racks with these thousands of dollars spending on that. You can grab your laptop with thousands of CUDA cores or whatsoever, the AMD Radeon cores. You can utilize it to run, I don't know, like orchestras, record 2 orchestras, because you have all of the power with yourself, but you can grab it. It's mobile right now. If you have a desktop, okay, no problem. You can use as many cores as you want. This is the totally new experience we want to grant to the end users that will work on the top of the GPU audio ecosystem we plan to build in collaboration with the Pro Audio developers community. What's more, the thing is that things are going fast, and there is a Wi-Fi 6E standard, and it managed to run 1 gigabit per second bandwidth. So here we can actually do not utilize the Thunderbolt 3 connection we showed you today, or Ethernet. We can run these IPC components and these remote computing cases just within the air. We need only the 1 gigabit per second connection. So it also makes lots of user experience cases that you can run for your end customers. This is very important because, well, other companies, like big guys, I don't know, like Avid, Waves, and these guys, they're providing you the entire solution with high cost and that stuff. Imagine you don't need it. You can purchase a laptop with the new RTX 3060, $1,000. It will do anything for you. What's more, we call this feature, it's not rolled out into the release in production area. Well, we're a tiny startup, right? But we tested already this. We call it instant rendering feature, fast rendering feature. Imagine you have heavy projects, like tens or even hundreds of tracks running on the timeline, half an hour, 45 minutes, or 1 hour. With GPU, utilizing all of the cores, you can do the rendering faster than the CPU. And for this price of money, this price, you can do that as easy, because you can manage to run in parallel whatsoever effects you have. So again, this is something that CPU cannot deliver, CPU-based solution cannot deliver for you with the low price cost. Okay, you can purchase the Threadrippers. I don't know, like per $1,000, but there are 32 cores, or how many cores, even running at 5 gigahertz, right? So again, this is a question about the solution cost. With the GPUs, with the time we want to deliver to end customers, to all consumers, availability to render like ray tracing for video, but for audio, performing the rendering and bouncing and exporting projects faster in times and tens of times faster than CPU based. And there is one unique case. I can imagine that if you run reverb with the quite long tail, you cannot run it on a single core as efficient as on GPU. So that's why it will be rendered in times slower than on GPU. And a scheduler, the scheduler component, it not just utilized the parallelization within the algorithm instance, but also for each track. So again, all the threads and blocks, there are parallel for each track and channel within the track. So it makes a lot of sense that you, with GPU audio-based solution, you can render projects faster. And for some heavy use cases, when you're working for some studio post-production, I don't know, like making movies for big companies, where when the salary for each specialist, it costs a lot. You don't need to spend like half an hour of waiting or 15 minutes of waiting each time you're pressing the bounce button. And this is something that will be delivered just within the box. With this SDK, if you will utilize our own methods, and you will build the product on the top of the GPU audio. So again, as I said before, we plan to deliver the completely new user experience. And maybe you have some specific questions. Maybe Josh or
yeah, there are quite a lot of questions.
Okay, let's start. Let's crack it.
So quite a few of them were from like earlier in the presentation, but I'll just go through them. Wesley Griffin is asking, what sort of utilization of the GPU are you getting? Is the processing parallel enough to hide the GPU thread latency?
Sorry, I didn't get it. Could you start?
Is the processing parallel enough to hide the GPU thread latency?
Yeah, we managed to run within 1 millisecond latency, even with crashes. I'm sorry, we have YouTube videos without crashes. And yes, it makes a lot of sense. Yes, there is a PCI Express problem between the CPU-based solution and GPU-based solution. You have to organize the transfer over the PCI Express 3.0. The problem why other Pro brands still continue thinking about that, it's quite high latency. No, it's not. Starting with the PCI Express 3.0, you can wrap up to 64 megabytes within 1 millisecond latency. You can dispatch it, and you can do all of that stuff within this 1 millisecond latency latency and 64 megabits per second bandwidth. If you can wrap it everything, you can support this scenario. For PCI Express 4.0, it's like how many? Like it's 4 times more. For PCI Express 5.0, again, you see.
Yeah.
So yeah.
So I think the question of latency is kind of the crux here. This is what kind of everyone's interested in. So just so Pavel Kopot posted quite a few questions on the chat here. He's saying, why do you think all existing GPU APIs like OpenCL and others that you've mentioned introduce latency and PTX assembly does not? It's so strange why there is no general purpose low latency GPU API. So basically, if you found a way to do this, why isn't there already an API for this? This seems to be really weird. So he actually goes on to say, if low latency on GPU is possible at all, it's just strange that there is no straightforward way of doing this. So there are no APIs for it. But what basically another way of thinking about this is what bottleneck is causing it, because PCIe by itself must be pretty fast, right? So there is also GPU firmware running some code, the OS driver, there are GPU APIs. So where's the bottleneck there, and why do you not suffer from that?
Yeah, so this is a great question. I can be almost 100% honest here. Well, because we are a startup, we're backed by VCs, and this is innovation. And I spend a lot of money of investors making this sort of stuff. But actually, this is one of the few questions that open the doors for the GPU audio implementation. What I can tell you is that, well, there are some methods you can utilize in OCL or CUDA, like work groups. They were recently introduced in CUDA 9 or something. And also there are overlapping feature and a synchronous feature you can utilize to organize something. At least you can deliver one ping pong stuff quite fast, but not every single time. And I cannot answer this question, how you have to organize it continuously, because it's actually the technology implementation, sorry. The second thing is that the working groups is the way to organize payloads on the device side with different blocks threads configuration. So you can do that with work groups on the CUDA or OpenCL, but you have to add something more than that if you plan to run like literally anything on the GPU, like any sort of the plugins, third-party developed plugins at any time you want to run it. So again, all of the answering all of the question, you have to implement what we call scheduler again. So the scheduler is one of the answers why it simply was not possible to do with generic APIs, and why these methods are not well presented in the API still. Maybe with the time, NVIDIA will produce some sort of the approach of scheduling these things, and they will develop some additional APIs to organize everything. But you can do, I can be like 100% honest here, you can do or low latency stuff, but not so much like 4 streams or 10 streams on the CUDA with a generic API. Or you can do some one-typed many instances payload running on the device, but you cannot do this simultaneously without going to the PTX ISA level. So again, the scheduler have to be implemented somehow by NVIDIA, by GPU audio team, whatsoever. You have to provide the full control over the resources, starting with streaming and finalizing how do you want to treat your processors with how many blocks and threads. So yeah.
I'm sorry, may I add my 2 cents here? So basically, to summarize what Sasha said, the, so to say, metaphysic, the part of the question, why the currently generic purpose APIs doesn't have those kind of abilities. Basically, it's history. As we know in computer science, it's always latency versus throughput optimizations, and the GPUs historically was used as high throughput devices. So all the APIs are constructed in this way, but this doesn't mean that those devices can be used another way. And that's why where we come in. Thank you.
Thank you so much for the thorough explanation. I just have a couple more quick questions about this, and then we move on to other questions. So how much of the GPU are you actually using? Like how much of the utilization?
You mean what? How many GPUs we support?
No. I think how many? I'm not actually an expert. It's a question from the chat. I guess how many of the available threads or something like that? Like,
yeah, all of them. For example, for the latest GPUs with tensor cores and that machine learning stuff, they have more than just CUDA cores, like more than 6,000 or 8,000 of cores. You can actually add some machine learning tensor cores to do some machine learning stuff, cool stuff, convolution, neural networks and that sort of things. So yes, we can utilize all of them. We don't need, we can control 100% of the GPU. That's the reason. And that's why the reason I mentioned this cool feature, we call it faster rendering, instant rendering, because we can utilize all of the cores if we have well-parallelized algorithms to render heavy projects really faster.
Okay, thank you. You mentioned,
sorry. I'm sorry. Just another 2 cents from me. Just for example, of how much in the current web demo that was presented today, each track from the DAW utilized 96 threads from the GPU.
Okay, I think that was exactly what was asked. So thank you so much. There was another thing. So you mentioned 1 millisecond at some point when we were talking about latency. The question is that round trip or is that dispatch?
No, round trip. We do within the buffer. We understand how it's important. We don't add any additional buffer. So yes, we are utilizing to offload from the memory of the client, from the BST plugin to the IPC connection to the TCP IP stack, using the Thunderbolt 3 USB-C connection to another GPU, dispatch it on the GPU server to the device, compute on the device, and return it back using the network and all of the components. Yes.
That is super impressive. That is super impressive. It's quite mind-blowing. Thank you.
Yeah.
I guess there was another question, kind of more general, like, what are the advantages of using the GPU for audio kind of in general? Are there really enough things that require this kind of parallel processing to like get a significant performance boost from what you're actually doing? Like, you know, as someone who's like practically, you know, making music or something like that?
Yeah, this is like the most popular question from the pessimistic part of the community, because, okay, like some of the users, they don't face two basic problems like dropouts, because of they cannot run many instances in low latency, so they have to increase latencies to avoid the dropouts, right? And if it doesn't have these problems, the question here arises like, I don't need it because I don't have this sort of problems. I don't need to offload from CPU and utilize my GPU, right? Yes. But you know, if you run, I don't know, like Abbey Road chamber or something like that, 70% CPU usage per single instance, right? If you run complex products like synthesizers, I don't know, like Omnisphere, you have to add more latency just right out of the box in order to deliver the result. Like for the Omnisphere, how many? Like 2 milliseconds, right? Yeah, 2 milliseconds you have to add in order to process it. So if you want to run within 1 millisecond latency, it's 3 just virtually in the program stack, and then it's added like hardware I/O and that stuff. So we're not just accelerating, we're not just offloading, we're also providing more features like instant bounce feature that we will introduce in the future. We also introduce unique use cases. You can upgrade it. You can upgrade CPUs for sure within the socket, right? And the PCI Express, it's not you know, the thing that is upgraded each year like a socket, and you can simply sell and buy the new one. And also we provide the solution for the remote computing feature. So again, here I see lots of the applications in many different fields, like recording in order to lower latencies and to you know, to have to do not pay latencies by CPU, but by GPU. It does nothing currently while recording, so why not applying the effects while do the low latency recording stuff, because it's, well, convenient way to do the recording in the studios. For the live concerts, again, the latency, you can bring all of the stuff, like all the racks, I don't know, like any sort of hardware solution, or you can bring the only laptop and it will handle all of that. For the post-production, if you're rendering bounds and exporting heaviest projects, you can do that easily with many cores of many GPUs you can utilize, right? And again, this is not so price hungry. So regardless the mining time, you know, because, well, currently with laptops, again, it costs like $1,000. You can purchase the RTX 3060. So many fields of application, and I think that there will be lots of pessimistic people that don't want to utilize it. Again, I do understand that people who spend tens of thousands of dollars on, I don't know, like Avid Pro Tools and hardware stuff, they will not switch to the GPU audio, definitely, because they invested into it. So that's the reason we came to the how to say, the most enthusiastic and innovative community that see the future. And we believe that the power of the GPU is the future for the Pro Audio, as well as the future of the new, more complex devices and processors and plugins. Because as you guys know, RTX voice.
So here,
Yeah.
I think it's a question. It's another question which kind of goes with that really nicely, which is there are actually other attempts to have programming languages that kind of exploit forms of like hardware acceleration or like domain-specific hardware things for audio, like in particular FOST and Soul, which are domain-specific languages that target, among other things, also potentially GPU audio. Have you looked into this? Have you compared what you're doing to Faust or Soul? Have you talked to them? Are you aware of these other technologies?
Yeah,
Sasha, would you allow me to handle this one?
Yeah. Please,
okay.
Please do.
We didn't contact the Faust or the Soul team yet, but we are well aware of them. I'm personally monitoring them. Another thing that I don't know, it was mentioned in the chat or not, just recently the HPVM 1.0 was released, and it's another thing from the same field. It's basically an LLVM-based compiler for CPUs, GPUs, FPGAs, and everything. Currently, we do not support. Our SDK doesn't support Faust or Soul or anything like that. Why so? Because as Sasha mentioned, the first and the main challenge that we faced is that we need a technology, this PTX-ASA code, which allows us to execute those things in the matter that is needed in the audio DSP. And then they know the sort of assembly that runs this good. Then we can think about compilers or translators that produce such code. So it's kind of one of the next steps. What probably will come, yes, because it's very promising. It's very promising.
Yeah, I agree. That's very interesting. So Josh, how are we doing with time? We have like a few more questions. I'm not sure if we should wrap up or we have time for them.
Maybe we can go for a couple more. Seems like quite a few people are pretty stimulated by this conversation. So I think let's keep.
So I have like 4 open questions still, and I think they're all pretty interesting. So I think it's worth spending just a few more minutes on this. So one question is by Hyper Eon, who's asking, how do you compile the audio code to run on GPU? And he says, like, sorry if I missed that explanation earlier. Like, as a developer, would you as a user of your tech stack, would you be supplied a compiler, or how does that work?
Okay, so basically, if you want to use our GPU audio SDK, will be published in the future, you need to have the CUDA only. Now, for the NVIDIA and for the AMD Radeon, I'm not sure what it is. Well, it will be like the Hippify solution. I cannot disclose it yet because it's also a part of the innovation. So you have to compile it using the NVCC and CUDA code. There will be standard CUDA primitives you can utilize and write down just a simple CUDA code. If you want to utilize our own implementation of all of the DSP libraries, FFT, whatsoever, you can use it. You can include in your C++ code and just utilize the calls. It will be pretty straightforward. But in case if you feel yourself strong and you think that you can manage all of the threads and blocks and parallelization stuff, you would be also able to do that right within your code. And then you will produce like Q binaries or PTXs you can utilize and run just like that. Just put it into the program files and it will work.
Okay, so Edward Boraski is pointing out in the chat that there is actually a good GPU DSP library from NVIDIA. It's called QSignal. Is that related in any way to what you're saying?
Yeah. But the point is that you cannot utilize them directly, because if you want our technology scheduler, to manage different instances of different developers, third-party developed plugins, you have to, or you or we have to re-implement the Q signal, Q blast, whatsoever for our GPU audio SDK, which we will do with the community in order to, to allow all of the features work. Because if you will not migrate that, for example, instant rendering or some things will simply not work, it will crash and that stuff. So you have to migrate it. And we will also write down the, how to say, technical framework, how to migrate the components for the GPU audio SDK, so everyone can contribute into it.
Well, that's great, because there was another question.
I'm sorry. May another 2 cents from me. So basically, to get the picture of this, there is a Q signal. Can it be used with our SDK? Well, yes and no. We can somehow. It's similar if some code or some plugin were developed on a raw BST standard, and we want to port it to Juice, for example. It can be done. They are both in C++, but the APIs are different. So when the processors are being written for our SDK, the code is it looks like just like any CUDA code, but it calls and utilizes additional APIs that are our scheduler APIs, which brings all the good features what we have. Because if we can surely just use the Q signal library directly on the GPU, and there are actually some quite a good algorithms, the aforementioned IIR filter, for example, but still there will be a problem how to run 100 of them simultaneously, or 10 IIRs and 10 FIR filters and so on. Thank you.
Okay, thank you. There's one more technical question from Pavel Kopot, who's asking, have you done some benchmarks that we could look at? For example, how many like microseconds, if you have a 70 thread delay, for example, something that we showed you, and then you're processing that with like 256 sample buffer size, like a buffer size of 256 stereo samples. Like, how does that then scale? How does that change if you add like 100 of them, etc.?
So I love this question. So there are two different environments here, and I'm 100% brutally honest with the community from the very beginning. There is the production area, and the BST standard is quite old. It aims to support everything, but it doesn't support the innovations. And it brings a lot of problems for people who are bringing something totally new to the industry. So we are managed to run like 150 of instances in the VST part or the GPU per 1 millisecond latency on my RTX 2080. But in the test area, without VST processor and that sort of things, I managed to run 700 of delays with the infinite impulse response filters within 1 millisecond buffer, within the 1 millisecond buffer latency, 700 on GTX 1070. So the technology, the core technology, the scheduler, we improve this constantly, and we improve this number of running simultaneously of all of the different plugins without the VST part continuously. So this 700 number is not the final one. I think that we can hit for the 1070 up to 2000 of delays. So this is something we done in the test area, but in order to bring it to the VST, we have to get the, we have to figure out how to control the CPU threads of the door, because they simply sleeping and doing nothing, and that's a big problem for us. But I think that we know how to manage them, because we recently had some call with Steinberg, and I think that they will help us to deliver the final level of performance to the production area, because, well, why not? And this level of bench performance, this could be extended over the new devices coming, which is great, because you don't need to do anything else. You write code once and it will work for the RTX 2080, from the GTX 1070 to RTX 2080, RTX 3090, whatsoever. Many CUDA cores, many RTX Tensor cores, more power, more performance, faster results, lower latencies, or lowest latency at all, just bring more instances. So yeah.
Right. Thank you. So I guess one kind of very direct question from Jacob K. Guitars: how mature is this technology?
This is mature enough to run the beta program, I hope, this summer. We actually announced to run this in April, but we are not managed to register the intellectual property first. And we are not going to deliver any binaries outside of the company unless we will register that, because, well, we spent 5 years on it. Sorry.
Yeah, of course. Yes, that's very sensible.
We will do that. We will open it, and I think that the time period to deliver from beta to the production to the commercial version will be like half a year. So I think that in the early 2022, hopefully we can deliver the commercial version that will work on different hardware setups of many users, and we can run different types of plugins. Also, we are making the multi-layer synthesizer. So
okay. Yeah, thanks. Well, I'm sure we can. Can't wait to see this actually out in the wild. Like, this is really exciting technology. So I guess to wrap up, I have one last question, which is, where can we learn more about this? Do we have a website? Do you have a blog? Is this documented anywhere where people can read up on how it all works and everything you talked about today? Like, where should people go? Where's like more info?
Yeah, so currently we published the gpu.audio website. Please follow this website, sign up for the beta if you want to receive the beta and help us to deliver things faster. If you're the developer that is really interested in opportunity to bring the GPU audio powered product with the time, and first of all with collaboration, because the technology is very complex and we want you to help you for free to deliver your version of the product, new product, or product that exists already, please also sign up for the SDK request following the gpu.audio. And soon we will open the corporate web blog and we will post everything there, and you guys can follow this blog. I will also announce it. Actually, if you guys like the Audio Programmer YouTube channel, if you allow us, we wanted to, to start delivering the beta with you, if you allow, like within a couple of months. It can be another episode of the Audio Programmer, so we can both discuss how it works, how it can be run on different DAWs with different types. So yeah.
Okay.
Yeah,
that would be amazing.
Great.
So just to everyone, the address is actually gpu.audio. Is that correct?
Yeah, we own this domain.
Okay, great.
Yeah, this is that address. Yes.
Awesome. Well, that's very promising. I'm sure we were looking forward to actually learn about the beta phase and see if you actually have a bit more to show in a few months. And I think it's going to be super exciting.
Yeah. We wanted to share with the community that soon we will release the video, and we will share it across our social media accounts. We actually do not support them well. I'm sorry for that, but soon we will release the video where the GPU nails the CPU in terms of application of reverbs, because, well, this is well parallelized algorithm and we want to show you all of the benefits of the GPU audio technology. Stay tuned. Thanks a lot.
Thank you so much for being with us tonight. And yeah, this is super exciting stuff.
Oh, I'm on mute. Yes, thank you very much to the GPU audio team for that fantastic presentation. And Yeah, it seems like some real groundbreaking stuff, and I'm looking forward to us having some future collaborations where we'll be able to share more.
Yeah, looking forward to it. I believe that the audio programmer community is a top-notch community. You guys actually do the great job. You're uniting people that are willing to bring more audio plugins, commercial, for free, whatsoever, to learn more about the programming part. And we're definitely looking forward to partner with you in the future.
Amazing. I can't wait. Great. So thank you once again to the GPU audio team. And also another quick thank you to our sponsors, Juice, Sonics, and Focusrite, for helping to support the Audio Programmer Meetup. Once again, if you want to continue this discussion, you can join us in our Audio Programmer Discord. You can find us on the audioprogrammer.com/community. So shifting gears now to something that's maybe a little bit lighter, we have our guest for Beyond the Code. So Beyond the Code is a talk that we do monthly where we just discuss about people and what they're doing and products they're coming out with, their views on coding, their views on C++, products they're releasing and the visions behind them, just trying to find out a little bit more about perspectives on audio programming. And today we have Paul Carter with us, who is from England, but actually way over in the Bay Area. How's it going, Paul?
Going well. Can you hear me?
Yeah, we can hear you well.
Thank you.
Yeah,
thanks for inviting me to join you guys. It's a great community. I'm sorry I said guys, and that's another thing I should be more careful about.
Yes.
Thank you so much.
Folks.
Yes.
Folks. Hi,
Yeah.
folks.
Yeah, so this is something good. Yeah, let's touch on this very, very quickly, because I think it's something that's so I do it all the time, and I'm trying to.
It's a bad habit.
Yeah, it's a habit, but especially if English is a second language, we find that there are a lot of people that when we just talk about people, we tend to use the word guys. And what we're trying to do generally in our audio programmer community is trying to get more people, more women and involved, and other people that are just not the main demographic of what we have in our audio programming community at the moment. Sorry, that's my dog, which is predominantly white males. So what I tend to do is I tend to use the word like everybody. Some people like to use the word folks, which I find doesn't really roll off the tongue very well. But I tend to try to use that rather than saying, hey, guys. I try to say, hey, everybody, or hey, folks. So that's something that I think is a good thing maybe for all of us here in the audio programming community to maybe try to employ a little bit more in our everyday language. I know it's something that I'm working on, trying to work on every day.
Thank you so much, Josh.
It's actually something that I only picked up since I moved to the States, because I never used to say that ever.
Yeah.
But everybody uses that here. It's very difficult to get out of the habit.
Yeah, it's so natural. It's so natural because we've been kind of saying it all our lives, haven't we? And I wasn't even aware of it until quite recently, that it's something that that sometimes makes people feel like they're not included in the conversation when we use the word guys, or when we tend to if we're talking about a person in a hypothetical situation, if we some people tend to use the male gender to describe that person rather than that person or they. So it's just something that we I think can just try as a community to improve upon. And we do it in our audio programmer Discord. Whenever somebody says, hey guys, we actually have a bot that pops up and says, can you just please use something that's a little bit more inclusive, like hey everybody, hey folks, or hey people, maybe. So hey audio programmers, how about that? Great, fantastic. Anyway, on with the show. So Paul, so you're over in the Bay Area, but you come from England, and I know a little bit more about your journey, but I think that it would be great just to hear a little bit about you, how you've got out there, a little bit about what you do, a little bit about, yeah, maybe we can just start there before
A very long story. I'll try and summarize it briefly. It's a pretty long story.
Well, remember, you got to be off in an hour, so
yeah,
we got to keep these things short.
Yeah. So, I'm actually from the UK originally, and cutting all my preschool history and school history, I was studying at university in York, and I did an electronic engineering degree with music technology systems. And that's where I first got into audio programming. And the very first thing I did there was some C++ coding for like MIDI handling, very basic stuff. And then I was lucky enough to get a placement at Texas Instruments in France, where I was doing DSP hotline support. And in that year of placement, I was able to pick up some knowledge on DSP coding in assembly language. And the project I did for my year in industry was a very basic guitar audio effects processor on a TI C54X DSP, which later I extended to be a 4-operator FM synthesizer for my final year project. So that's kind of where I started with DSP coding. I've always been interested in music, and I played piano since a young age, and always was into synthesizers. And my first synth was a Korg wave station, which has inspired me a lot in the things that I'm doing, and I'll talk about in a minute. But I had a long period of not doing any audio coding, where I was in the consumer electronics industry, just working on digital radio products, developing user interfaces or data processing code for decoding signals like program guides or scrolling text, that kind of thing. And I actually moved out to Hong Kong, and I was there for 7 years, running a small team of engineers. We were doing consumer electronic products like DAB, digital radios, CD players, Walkmans, that kind of stuff. And the reason I got into that side of the industry was because the company that was making those radio receivers was using Texas Instruments DSPs. So that's the link, and that's how I got into that company. And after some time, the British company I was working for closed down, and I switched to an American company doing a very similar thing called IBOC, Inbound on Channel. It's a HD radio standard in the USA. And after a year or so of doing that work, and that company was based in California, very close to the Intel office. That company actually got acquired by Intel, and that's how I found myself working for that company. I did embedded development. I did Bluetooth drivers. I did wearables. I did field support for embedded products. And the wearables group shut down, and I moved into another group, which was an advertising group, where I got to start working on audio again. I got to start working on sound generation and sound processing code. And the main purpose of those products that we were, or those tools that we were developing, was for interactive displays, audiovisual interactive displays, and VR experiences, AR experiences. And so I had the chance to develop a modular audio processing engine, which was used for those interactive displays and VR experiences. And it's because I needed to develop that kind of code that I got into Juice and picked up Juice and worked with some experts that had, you probably would have heard of Matt Teitel, and I know you know Roland Rabian.
Yeah,
those guys helped me to do. Those guys helped me to do some of the work I did for that tech company, and so I picked up a lot of knowledge from those guys and from those people.
Well, they are guys.
They are guys.
They are guys in this situation.
And I really learned a lot for about a year or so developing synth code and interactive audio experiences, as we call them.
Yeah.
They're the kind of things you see in the Intel lobby. We have a massive interactive display panel with RealSense cameras. And we also do things like detect emotions or skeletal tracking through AI. and we use those inputs to drive the music and the sound. My department, unfortunately, was shut down again. And so I was on a 3-month notice, and that's really what kicked off my project, Hyperion. And I just thought I should really use my knowledge that I've gained here to develop a product that I can use for one thing, maybe to make money, but also to prove my knowledge and potentially find another job in the future.
Yeah. So let me. I'm going to share the screen just to show the actual product that he's just released, and it's been brought out in cooperation with the good friends at Traction. So big shout out to the team at Traction, Roland Rabian, Dave Roland, and the rest of the team. Woody is out there as well, and of course Jules, who is extended family now. So yeah, so you can see. So if you're watching this, then you can see the what Hyperion actually is. But I'll let you just describe what it is, Paul. If you could just describe what people are actually seeing here.
Yeah. So Hyperion is a multi-layer modular synth. You have control nodes and voice nodes, and all of those control and voice nodes are polyphonic. So where you see blue and orange nodes there, what's actually happening in the background is that there are up to 16 copies of those running for each voice. And then if you were to scroll down in the UI, you would see potentially effects bus nodes, which are something, well, you won't see it necessarily here, but the green, yeah, if you will actually do scroll down that page, there's an example there. You'll see effects bus nodes, which basically are taking the summed output of the audio output node, which is the mix down of all the voices, and processing a mix down as an effect. The idea for Hyperion for me was to make something that was modular but fairly easy to get to grips with. And I mentioned the Wave Station earlier, and some of the features of Hyperion are kind of inspired by the Wave Station. The fact that you can add multiple layers and then you can do key splits and velocity splits or assign them to different MIDI channels. That's a feature that I really liked in the original Wave Station keyboard. And yeah, I just wanted to extend that and make it much more powerful. With Hyperion, you can send data between each of the layers. So you can have up to 10 modular patches running in parallel. And you can also send effects bus audio between the layers. So, if you wanted to, you can have a layer that was just dedicated to effects bus processing only. And Hyperion also has some data processing nodes and data generating nodes, which let you send out MIDI data either to other layers or to the external world. So you could drive other synths from Hyperion's generative nodes.
Wow. And yeah, this is a project that you've been working on for quite a long time. So I think that we met either a year and a half ago or 2.5 years ago. We couldn't really agree on when it was. I'm pretty sure that it was 2.5 years ago at the NAMM.
Yeah.
About.
I think I've attended 3 NAMM shows now in person.
Yeah.
And the very first time I was just figuring out how to do this stuff, just trying to build my own plugin. And the second time is when I met you, and then you kind of introduced me more to the Traction team. And they've been really good. I think it's worth explaining that I have a day job and I don't really have all that much time to figure out all the commercial aspects of making a plugin, how to release it, how to sell it, how to do things like license checking. So I was really pleased to get some support from the Traction team. They've got a program called Traction Presents, and they basically helped me with the unlocking mechanism and helped me with basically just putting the software up there and selling it for me. And so I would not have the time to take care of all that kind of thing, all the marketing. Although I do try, I make YouTube videos, and I try and self-promote as much as I can by telling people about the synth. And I have my own webpage. So if you were interested in finding more information, you could go to hyperionsynth.com. And also I kind of have a portal page, which is wavesequencer.com.
Yeah.
Where
Yeah.
I hope to release future products other than Hyperion maybe one day. But we'll
Well,
see. This is the first one.
It seems like you have enough DSP to release another 100 years worth of products. So, touching on the DSP, was this DSP that you wrote from scratch for all of these, or did you have bits of DSP that were lying around that you curated and compiled to make this? How did that manifest itself?
So the node processing architecture, the way that nodes are processed and traversed, is all custom code. Mm-hmm. It's just something I came up with. There are nodes and there are pins, and they're connected to each other logically. There's just a list of processing nodes that is traversed each time the audio callback is triggered. So I developed all that code. I also developed the multi-processing side of things. So it's actually a multi-threaded implementation, so that each voice runs on a separate thread that's basically a thread pool that's pre-allocated. So every time you get an audio callback, the chain of nodes for every voice is executed on a separate thread. Mm-hmm. So it's really, the aim of Hyperion was for me was to make it super powerful, but also super low CPU usage. Mm-hmm. So if you've got like a 16-core CPU, it's going to use all the cores available, and it's going to really be super low CPU usage.
Yeah,
but in terms of the DSP code, most of it is, and I'm not a DSP expert. I said I worked for TI in the past, but I'm not really a math guy. So what I tend to do is I'll look at open source MIT code, and I'll grab bits. I'll look at existing filter implementations, and I'll tweak them. I'll change some settings, and I'll just get them to do what I want them to do. But I'm not necessarily writing them all from scratch. For things like the reverb algorithms, I did develop my own reverb algorithms, but I used some off-the-shelf MIT comb filter and all-pass filter code, and then I just chained them up in a way that I thought was interesting, added some modulation with some LFOs, and the same things for like chorus effects and flanges. I just used some off-the-shelf delay circular buffer code, and then just tweaked it and arranged the processing in a way that sounded good to my ears. But I'm certainly no DSP guy, other than I know how to put things together so that they'll process the audio and spit out some sound. So I tend to be an experimental developer. I'll just find code and hack it until it sounds good. So there's a lot of iterative development work going on here. And I've been hacking away at this for 2.5 years now, over many nights and weekends.
And what would you say? So there's a lot going on here, because you not only have the nodes, but you also have a lot of functionality that one would associate with a DAW. So being able to save patches. Looks like you have a lot of mouse controls there in the top left and top right. And I'm curious to understand what challenges that you've had creating a whole environment for this, rather than just having, because it is a VST, but you also have it as a standalone version as well. And
yeah, it's a standalone, but there's no sequencing involved here. It's simply processing MIDI input data and then sending it to different layers. Each layer is, although it sounds like it's complicated, each layer is just a new instance of the plugin effectively. If you could think about it that way, it's basically every layer is its own synth plugin with its own MIDI channel handling, MIDI data handling, with its own voice handler, with its own node list. So every layer is also processed on a separate thread if possible. So not only are the voices within the layers multi-threaded, but the layers themselves are also multi-threaded where possible. But really, it's I started with one layer of processing, one node tree or one node list, and it's not particularly complex to then extend it to multiple layers. The hardest part for me actually was the GUI and coming up with a way to patch cables and have them connect and disconnect in a sensible way, and then have that also reflected in the audio processing without causing glitches. And that was quite a challenge. And I didn't use any of the Juice tools for that. I didn't use the value tree or the what is it? The audio. I think there's an audio chain that you can use in Juice.
Yeah, the
I
audio
didn't use
processor chain. Yeah.
Yeah. So I just did my own custom thing where I just have lists of nodes, and each node has its own audio process buffer. And when you connect one to another, it's basically that each node stores a pointer to the pins that it's connected to. And if it's an audio source pin, then it can read the buffer directly from that other node. So every process block, it just goes through the node list, and just each node looks at its inputs and says, do I have a pointer to a buffer in another node? If so, bring that, process that audio in my audio buffer. And then the next node is processed, etc.
So can I ask you a question about this? So what is actually the advantage then over doing this over like the Juice thing?
There is no advantage other than the fact that I didn't really know about the Juice way of doing it at the time. And I figured it would be good to try and anyway do it myself, because I'm learning something here. I'd learned a lot to do this by myself. And also, I'm thinking, maybe in the future, I might potentially want to port this code down to an embedded platform. I might not want to use the Juice API. So, where possible, I don't use Juice. I do use Juice for the GUI, obviously, and also for things like a JSON file, which is, the format I use for storing patches. I use other Juice classes like the DSP oversampling class. But that would be easily replaced with my own code if necessary.
That's interesting.
So I'm just thinking, with portability in mind, to bring it to other platforms in future, maybe. I mean, I would love to make a hardware synth. That's kind of my ultimate goal. But this is like the intermediate step.
So because there are quite a few other Juice classes as well that I think quite a lot of plugins use, like the audio buffer class or the value tree, which quite a lot of applications written in Juice, they make that like the center of the data model. So you're not basically using any of the stuff.
I'm not using the audio buffer class. I am using the Juice MIDI classes, so the MIDI iterator, MIDI handling. I am using Juice for that. So in order to receive data or pick a MIDI input device, I am using the Juice classes for that.
Do you use the
I am
tree?
using the Juice, of course. I'm using the Juice process block calls, like prepare to play and process audio, and all of the VST related functions like where it loads the state and saves the state. So that's that's all standard stuff that Juice implements. And I wouldn't have had the time to figure out all of the VST-free API side of things, or the AU API. So that is where Juice has been super, super useful. But if I were to go and port this to a hardware product, then I guess I don't need the VST-free API in that case. So all of that stuff can be removed. Another reason that I have this approach is because of the work I did for that company I mentioned, where I'm actually developing similar kinds of audio processing code, but for game engines, where the system audio callback and maybe input notes don't come from Juice. They don't come from Juice's MIDI handling. They come from Unreal or from Unity. And so I am doing similar kinds of modular synthesis, but basically all of the code is just the node tree system that I developed, and it's being triggered by Unreal or Unity audio callbacks.
So you're basically kind of using Juice wherever Juice interfaces with like some third party or like operating system APIs that you just absolutely have to use, like BST or AX, AUV, like that kind of stuff, or like the graphics, but like everything that's kind of internal in your code, like inside this kind of wall. You just use plain C++, you just write things from scratch, or you use other like third-party open source libraries?
No, it's all from scratch, other than, like I said, I'll reference some MIT open source DSP code for things like filters, and effects. I did reference those, and then I'll hack it, change it, and write my own effects, basically.
So that's please let me know if I'm like too curious now, because now I'm like the coder in me is like, oh, so how do you like so
one resource I can recommend is Nigel Redmond. Like if you want to learn about wavetables, you can look at Nigel Redmond's stuff. I think his website's called Ear Level Engineering. And you know, I've built my own sort of custom oscillators that are similar to the way the Wave Station keyboard does it with wave sequencing, where I would crossfade between oscillator configurations. You know, and I just actually, you know, for example, the plucked string oscillator is actually a piece of Juice. I think it's originally from the Juice demo code. There's a plucked string model in the Juice demo code, and then I just took that and hacked it. And
oh, I remember it. I wrote
it.
that. I wrote that thing when I was applying for a job at the Juice team, which
Awesome.
was I don't know how many years ago. I wrote that thing because they wanted me to write like a demo app. So that was the thing, the plug demo
that
thing. I remember that.
Great,
yeah, I wrote that many years ago. That's funny that you bring that up now. No one has ever brought it up until now. That's really funny.
That's correct. Yeah, the plucked string model, but I extended it so that, you know, it can handle polyphonic note input, and so that it can handle pitch bends, and it can handle unison detune. So I have a model with all my oscillators. I can basically add detuned copies for doing unison detune, and you can, you know, control the stereo spreading of those unison detuned copies. So for the plucked string oscillator, I've got the same thing. You can basically add detuned copies of the plucked string oscillator, and it is literally just running the algorithm multiple times for each oscillator copy. It's not a chorus effect. The same with the oscillator code. It's just super efficient code, and I think the fact that it runs on multiple threads means that it's actually feasible to run many oscillators at the same time on many layers.
Amazing. Timer's going to be looking for his royalties.
Okay, one last coding question, because I'm just really curious. So a lot of people use the Juice value tree to like basically hold the whole state of their app like in place basically and manage like the state. So if you don't use that, like how do you do you have like your own data structure? How does can you just say a couple sentences about that? Because that's actually a really complicated problem if you have like a complicated plugin.
It is complicated.
So I just want to know how you solve it.
You know, I have a list of nodes, and they are the processing list that's used in the sort of the core processing. But then I have like a mirror of that list of nodes, which is just the UI node tree. And that's only for one voice, because when you're turning a knob in the UI, you're only editing kind of like a global parameter like the filter cutoff. It affects all the voices at the same time. But what's happening is that mirrored copy of parameters is then every time the audio thread gets called, it just reads off the values from that UI value tree. And so there's no blocking going on. When I change a parameter in the UI, it's just changing parameters in the UI-based node list, and they're just grabbed every audio frame. So that's how it works, pretty much.
Cool, thank you. Yeah, that makes sense.
Yeah, very cool. And what are you using?
Things like adding and removing nodes, those are done by instantiating all of the node data and the node object itself, like the code that runs the node. Say if you wanted to add a filter into the graph, it creates the object, and then it says, okay, I'm ready to add it to the audio thread. And then in the next audio process block, it sees that there's a flag to say, hey, I've got a new node to add. And then it just adds it to the list. So it's not doing any allocation on the audio thread. All the allocation is done in the UI thread.
Oh yeah, of course. Yeah, you have to do that. So I find that really fascinating, because like everyone who writes audio plugins has this problem, and everyone solves it slightly differently. I find this like super fascinating.
Yeah, amazing. I think we should do a demo of it really quick.
Oh yeah, if you've got the YouTube link, let's hear a quick demo.
I do. So here we go. Wow. Pretty nice.
Don't play
That's
the whole thing.
super cool stuff. Super cool
Goes
stuff.
on for 15 minutes. So, but yeah, please do, if you're interested at all, go check out the videos on the Hyperion YouTube channel. And there's links to all of these sound demos and also some SoundCloud tracks on the HyperionSynth.com website. And also, you know, a FAQ and features list and information about how to go buy this thing.
Yeah, absolutely. And we'll make sure that we put the links to this in the description as well, in the video description afterwards. So did you do all the presets yourself, all the sound design and all the presets?
I would say like 99% of the presets are my own. I had a few beta testers contribute a few, so I have added those in, the ones that were quite good. But yeah, 99% of the presets there are my own. There's around 450 presets, and not all of them are sound presets. Some of them are generative patches, or they are aux bus only. So they're just a list of audio processing on the aux bus. So I have a node which is a aux receive node, and then you can just process the aux bus in a layer and only do that. And that's really useful if you want to save CPU time. So you can send audio from multiple layers to one single layer that's only doing the reverb. If your CPU is not that powerful, then you can just do all the reverb just on one layer. But there's nothing stopping you. And in most of my patches, in my combi patches, I tend to use reverb independently on each layer because I just like the way that sounds. I like to have the flexibility to have a short reverb on some sounds and a long reverb on others. Yeah, and you can basically patch up the effects any way you like. You can design your own sort of mega reverbs by combining multiple reverbs and mixing them together, and you chain up as many choruses or flanges or distortions as you want to. There's no limits to how much you can chain up, really, other than your CPU processing time. And I guess one of the other fairly no limit things is there is a limit to it, but in terms of modulation sources, I did have to set a limit, but you can connect up to 16 sources to every modulation input pin. And I think in most scenarios, most people won't use more than 16 modulation sources going to a modulation input pin. It's usually enough. I tend to only use 4 or 5 modulation sources, say, if I want to modulate the filter cutoff.
Yeah, amazing. And you had mentioned before the call about that you wanted to make this compatible with game engines as well. So what are the challenges of doing that?
So that's nothing to do with Hyperion. That's more to do with the Intel work. So that's just the side of the work that I do for Intel. It's interactive displays, VR, AR experiences, and the work I do there is all about showing off technology which is related to Intel GPU or AI processing. So the sound aspect is just a side part of the whole demo. It's really just a way of showing off something interesting. But one of the things I'm looking into is using AI to potentially design and generate sounds, and using it to potentially generate patches on the fly from trained data. So I can't really go too much into that. It's kind of secret stuff. So
yeah, would that be a V2 of Hyperion then?
No, I mean, that's, like I say, that's completely separate work. It's nothing to do with Hyperion. I see. That's my day job.
Yeah, very interesting. Cool. Yeah, I think I'm out of questions. Can you let people know again where to find more information about Hyperion if they want to get it, if they want to see the demos?
Yeah, actually, maybe you could play the other demo video I gave you the link to. But yeah, HyperionSynth.com is the website that I developed, and Hyperion is actually on sale at Traction.com. I can type those in if you need to. Let's see, Hyperion.
That's Traction with a CK, right?
Yeah.
Yes.
All right, I've got it.
So you're going to play a video which is just to show you, yes, you can use Hyperion as a classic synth plugin, but if you want to, you can also just develop generative patches, use logical expressions, scale mappings, and it can drive music and sound all by itself without you even touching a keyboard. So, you know, this is just I wanted to show this demo just to show you that it's not just necessarily a patch playback synth. You could design entire pieces that will just play by themselves endlessly with continual variation. And so there's a lot of things you can do with it. And as I said before, if you wanted to, you can drive external MIDI devices. You can send data to an external MIDI device, and you can pick the channel that you send data to. So you can send notes and CC data, and you can drive all those notes and CC data from within the Hyperion patch. So
Wow.
it could be, you know, part of a much bigger system. One of the things I like to do with Hyperion is just play. You know, although I do use a DAW and I make tracks sometimes, what I like to do is just sit there and play pieces. And that's why I like this multi-layer architecture, because I like to be able to set up sounds at different parts of my keyboard. I tend to have a big keyboard, like an 88-key keyboard, and I'll set up patches on different areas of the keyboard and at different velocities. And I see it as a performance instrument as much as a BST plugin. So you can use it in standalone mode if you don't want to use a sequencer, and just use it as a performance tool. And if you have multiple keyboards, you can even use different MIDI channels on your hardware keyboards to target different layers. So, you know, you could imagine having a stack of 10 MIDI keyboards and control 10 different layers from each keyboard, or one different layer from each, you know, of those 10 keyboards.
Yeah.
So I do have a question here. So I saw that you have in the patch that was just on screen, you had like some scale generators. They were going into multipliers. They were feeding into like LFOs and things like that. So I'm wondering, like, this is exactly the kind of stuff that a lot of people use Max MSP for like kind of generative music. So I wonder how they compare.
I mean, I think, you know, I hope it's okay to say, I think Hyperion is a lot easier to use. I think, you know, Hyperion tends to have ready-built blocks. With something like Max MSP, maybe it's changed now, but when I first looked at it, if you wanted to design an oscillator that had unison detunes and wave folding and phase onset control, stereo spreading control, you know, all these different things, you'd have to design a pretty complex patch just to make one oscillator. Whereas Hyperion has these sort of bigger nodes that do all of that for you. So say, for example, the scale generator node in Max, you might have to design a lot of math nodes around, you know, to make something that would map to different scales. You might have to make a big patch, but I basically made a node that does it all for you. So I'm trying to simplify the way to approach generative music and synthesis, but in a modular way, which gives you a lot of flexibility, but also, you know, means you don't have to be that much of a nerd. You know, if you want to use a reverb, there's a reverb node. You don't have to design a reverb using individual delays and filters, right? You don't have to lay out your cone filter architecture and control all the delays. You just use the reverb node. So it's a lot simpler to use, I think, than something like Max. Some people compare it to Reactor, and I would say it's also simpler to use than Reactor. It's difficult to say what you can compare it to. I didn't design it with competing with another synth in mind. I just designed it because I wanted to have a fairly approachable modular system that let me layer and split lots of sounds and have low CPU overheads. And it's just kind of organically grown based on the features that I wanted to see in a modular synth. And I like to produce music without thinking too hard about it. So I didn't want to make it too complex in terms of setting up new sounds. Yes, there's a learning curve to using it. Yes, you have to spend a bit of time to understand how you patch things up. But there are a lot of example patches there. There are init patches you can start with. And I'm developing some training videos where I explain the overall interface and how patching is done. And I hope that it does seem a lot easier than something like Reactor or Max.
Yeah. That's great. Do we have any questions from the chat, Teamer?
Just a couple. So someone's asking if you're on Twitter.
I'm not very good with social media, admittedly. I am on Twitter, but I almost never tweet on Twitter. So, you know, I set up the Hyperion website. I don't even have a Facebook profile for this thing, but maybe I should be on Twitter. I'm on Discord, and I am on the audioprogrammer.com Discord channels.
So would that be the best way to like reach out to you?
Yeah, probably the best way is to reach out to me on Discord. And if you go to the Hyperion Synth website, there's a link, an invite link to the Wave Sequencer Discord channels, which is, you know, that's my tag on Discord, Wave Sequencer, which is also the name of the website, wavesequencer.com, which is kind of my portal where I might be showing other products in future. So Wave Sequencer on Discord, you can join the server there, and there are channels there that are dedicated to Hyperion. And if you do buy a licensed copy, there are supporter channels there where you can have more direct contact with me and more help from, say, the rest of the beta team and the moderator team. They'll be happy to help answer questions when I'm not online.
Okay, thanks. There's also a question, could you also post the resources for wavetable programming that you mentioned earlier?
I did load a couple of YouTube demos on how to patch up some sounds, and one of them is a pad sound demo, and it's, are you talking about the so you're talking about the actual code resources, not so much designing a patch?
That's the way that I took that question.
Okay, so yeah, Nigel Redman, earlevelengineering.com.
Yeah, that was it.
Yeah, earlevelengineering.com. You can also look at Matt Titel's, I think it's Helm Synth. He's got some pretty good code that does wavetable stuff there.
Yeah, his Vital Synth is also, actually open source.
Yeah, and of course Vital's amazing. Totally different synth, but yeah, Matt's done an amazing job with Vital.
Yeah, if you want to see an amazing full-fledged professional synth that's built in C++, have a look at Vital, the Vital synth on GitHub. That will blow your mind. You'll see a whole bunch of stuff that you'll think, wow, what the heck?
So,
we need to get him on here.
I think I used a website called dsp-something.org. I don't remember the exact name of it.
I think that's
dsp.org.
Yeah, I think that's dspguide.org.
I'm not sure.
Yeah, ear level is really good. And yeah, ear level is a great one. And there is code around. I mean, even if you go in Google and just type reverb C++ code, you'll find some stuff. It's out there.
I mean, put it this way, there's enough MIT licensed source code out there that you could build a pretty decent synth from. The hard part is chaining it all together and handling all the things like polyphonic input, voice allocations, the GUI, patch databases, saving state, all of the other stuff. To be honest, I feel like the DSP side is the easy part. Although, you know, I'm not designing my own DSP code, but I would say that's the DSP, the audio processing side of it, is actually a small part of the equation in making a plugin. All the other side of things, and then you've got do you want to actually sell the thing? You know, how do you market it? How do you sell it? Like I say, that's why I went with Traction, because those guys really helped me out there.
And what would you say was the biggest challenge in making this project? Where were the parts where you were getting stuck?
For me, the biggest challenge was the user interface. Yeah, like I said, as I was saying, the audio processing code. You know, I'd had some background in playing with that kind of thing when I did a DSP-based project on TI chips, and that was written in assembly language back then. But you know, it was the same principles. You know, you have a callback, you have a certain time to process the audio in, and then you spit out some data. And I find that's not too hard to grasp, but all of the things like how to pop up slider boxes and how to draw curves on the screen and how to select multiple items and drag them around all at the same time, file handling, saving data to the disk. That's all stuff that I haven't really done until I developed a plugin, because most of my work has been on consumer electronic products where you didn't have that kind of experience. You had a basic GUI, but it was usually text based, where you had like maybe a few submenus that you could scroll through, like on an old iPod. Like remember the iPods with the dial? It was that's the kind of level of GUI that I was working on before, where you didn't really have any graphics. It was a user interface with just text and submenus. So and there was no concept of saving and restoring patches or files. You could save your radio presets to come back to your previous stations. Like on a car radio, you have presets 1 to 10. So that was the kind of level of user data management that I had to handle in the past. But it's much more complex for a plugin, and that's the part I found really hard.
Amazing. Great. I think we don't have any more questions in the chat, and I know that you have to run soon. So I think this is a good place for us to wrap up. Do you have any other questions, Timur?
No, I think we're good. We're good to wrap up. Thank you so much for your time and for these really quite interesting insights into this really cool product. I'm going to definitely check it out. Oh, by the way, I do have a question. Is there like a demo? Like a free demo?
Yeah, so you can download on traction.com. You can get an evaluation license. So you just have to register on traction.com, and I think it's a 90-day evaluation license. So the simple run for 90 days in evaluation mode. And then after that, you have to buy it.
But 90 days sounds plenty to wrap my head around it. So yeah, that's pretty cool. Thanks.
Yeah. I'm really interested in all of the stuff about GPU, DSP. I maybe didn't concentrate enough, so I'll have to rewatch the video later to really dig into learning about it. But when somebody said, why would you use GPU to process audio? Is it really a benefit? Can you really use all those cores? Yes, I definitely can. Every core I can get hold of, I want to use. So, if I had a 128 core processor, I'd be very happy. Every voice can run on a separate thread, and every layer can run on a separate thread. So that's a lot of threads and a lot of potential cores.
Yeah, I believe that if I can add my 2 cents here, I think that synthesizers, reverbs, and machine learning based algorithms are great fits for the GPU powered systems. So I think that if you have a heavy work delivered right into the time, I think that's a good opportunity for the collaboration. And I saw your request for SDK. Yeah.
Amazing stuff. And I think that's a great place for us to wrap up. So once again, thank you to our sponsors, Juice, Sonics, and Focusrite for sponsoring the Audio Programmer Meetup. And thank you to the GPU audio team and to Paul for joining us and sharing this valuable information. I think a lot of people are definitely curious and really inspired now. So thank you very much for sharing your time.
Thanks a lot. I believe personally, the Audio Programmer is just the great place where people can meet together and have talks on great topics. I personally love the idea of Paul making this modular synthesizer and the approach he utilized to organize the code, because I think that maybe are you using the graph approach to organize your computing, but whatsoever, I just love it. And I think that the Audio Programmer could be really helpful for people who want to bring cool stuff by watching how other guys bring in the cool stuff here. So it will, like in model systems, it can grow really big, infinitely big,
Yeah, the audioprogrammer.com is an amazing resource. And I only wish that it had blown up before I got into all of this stuff, because I had a ton of questions at the beginning when I was just first started, and there wasn't, yes, there were the Juice forums, but you kind of feel a bit intimidated sometimes to ask questions there, because there are some really expert programmers that sometimes, answer in a way that, might make you feel a little bit small. But on the Discord channels, on the audio programmer community, I think this is one of the things that Josh has done really well, is that he's made it very approachable, and people are not afraid to chat and ask questions and post dumb questions. And every level of engineer is there, from just starting to learn C++ to PhD DSP guys. So it's a brilliant resource.
Yeah, I can double that. It's a pity that audio programmer wasn't there 7 years ago when I started to research this field.
Yeah, thank you very much. But thanks to all of you for really sharing your knowledge, because it's really your knowledge and experience that really helps out the community at large. And people like Teamer, and all the talks that you've done in the community have been really influential on the next generation of audio developers. So I'm just humbled to actually be part of this, and just to have the opportunity to have you on the channel. I mean, it's very humbling for me. So thank you very much, and thanks to everybody who's also tuned in and watched through the presentations. It's been a really fun one. It's
been a fun one, and I feel the same. I'm so humbled to just be here and be able to talk to all these amazing people who are doing all these amazing things and learning about all of the stuff. It's super cool. I have actually 2 very quick things to say. One is something I already mentioned. If you want to give a talk at our meetup, you don't have to be a super experienced pro. You don't have to be like a super experienced speaker. If you think you have something interesting to share, something you've done, or something you care about, or something you're interested in, sharing, your own insights about with the rest of the community, then you are someone who totally should be on the show. Please let us know. theaudioprogrammer.com/submit. And the other thing is, our meetup takes place every month at every second Tuesday of the month. And so the next one is on the 11th of May. So please come again at the 11th of May. It starts at 6:30 p.m. London local time, which currently, because of British summertime daylight saving time, corresponds to 7:30 UTC, whatever that is in your time zone. So please tune in again next month.
Yes, and it can be a very big mix-up. We always have a big mix-up every month, because I think England must be the only country in the world where the time zone that it's actually in changes depending on the time of year.
Well, right, you have Europe where it's like CET and CEST, like Central European Time and Central European Standard Time. Actually, that's one great thing about Russia, because Russia is on daylight saving time all year. So it just never changes. It's always UTC +3. So it's very easy. But in Europe, it's just it actually gets really messy, because America switches to daylight saving time, but at different times. And then Australia also switches daylight saving times at different times and in a different direction. So,
but in the States, we don't call it different things, though. It's always EST or PST for Pacific Standard Time. It's never
okay.
Like we don't do it like.
So you don't have Pacific summertime or something like that?
No.
Interesting.
No. Yeah, it's never BST. Like England has 3: BST, UTC, GMT.
So UTC is actually an international standard. It's universal coordinated time. And then GMT is just another name for that. It stands for Greenwich Mean Time. That never changes. And then British, so the Brits are on Greenwich Mean Time during the winter, and they have their own time zone, which is called BST, during the summer. So yes, it is confusing. Anyway, time zones are hard. Yeah. I'm pretty sure we can get this right next month again. So please tune in.
Yes, thank you. And with that, we will sign off. So we will see you on the second Tuesday, May 11th.
The 11th, yes.
Great. See you later.
See you, and have a great evening.
Happy anniversary.
Bye.
Yay.
Thank you.
Yay. Bye-bye.